Previously, we've defined matrix vector multiplication. In this section, we're going to be looking at a way to multiply two matrices together, or looking at matrix-matrix products or multiplication. This operation is going to be useful in a lot of applications and will become especially important when we study linear transformations later in the course. So suppose we have the matrix B consisting of the columns V1, V2 through Vn. So, these columns are vectors in some space, maybe Rm, making B an M by N matrix, for example. And then if A is another matrix of a specific size, we'll talk about what size makes sense, then we can define the product A times B as the matrix whose columns consist of the matrix vector products AV1, AV2, dot, 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 down to AVN. So let's look at an example here. Suppose A is the matrix 1, 2, 0, negative 1, 3, 4, and B is the matrix 1, negative 2, 3, 0, 4, 1. Notice here that A is a 2 by 3 matrix and B is a 3 by 2 matrix. And let's look at their product. So we've got A times B. Just rewrite that out here. And I'll go back for a second so we can kind of break down the definition. So the result here is going to be what we get when we multiply A by each of the columns of B. So we might consider doing that sort of separately. So, AV1 in this case would be the product of A with the first column of B. And just to remind you how that works, that means we're taking a linear combination of the columns of A with weights equal to the components of B. So the result here would be 1 times 1, negative 1, plus 3 times 2, 3, plus 4 times 0, 4. And we put all that together. Notice that our result here is going to be a vector in R2. So we'd get 1 plus 6, so that's 7. And then we get negative 1 plus 9, which is 8, plus 16, so that looks like 24. So this AV1 is going to be the first column in the matrix product A times B. So maybe over here, we'll start to construct that. So this AB, rewrite that here, AB is going to ultimately equal 724 as its first column. And then we can do AV2 in a similar way. So maybe we'll just, let's write out A again, 1, 2, 0, negative 1, 3, 4. And then V2 in this case is negative 2, 0, 1. And so this is going to be negative 2 times 1, negative 1, plus 0. Doesn't really matter what I write here, but times 2, 3. And then plus 1 times 0, 4. So we work all that out. We get, again, a vector in R2, negative 2 plus 0 plus 0. So it's just negative 2. And then 2 plus 4 is 6. This is going to be the second column in the product, so negative 2, 6. So notice that AB is a 2 by 2 matrix, and we'll talk a bit about, as we move through the course, kind of why this is a sensible way to define matrix-matrix products. But for now, we're going to focus sort of on how that computation works. Same two matrices here. Let's see if we can compute BA, just as more practice, and also to sort of see if our kind of standard concept of commutativity, this idea that in real numbers and in a lot of other types of mathematical objects, when we multiply two of our objects together, it doesn't really matter what order we do it in. The result is the same, right? So, for real numbers, if you did 2 times 5, you get 10. And if you did 5 times 2, you get 10. The order doesn't matter. Let's see if that holds true for matrices. So we're going to take B this time, multiply it by A. And I actually want to, when I'm doing this, sort of highlight a couple of things. Maybe a way to sort of do these matrix multiplications, especially when you're doing them by hand, a little bit quicker. First of all, a little bit of a quick check here. B is a 3 by 2 matrix. A is a 2 by 3 matrix. And so if we go back to that definition of matrix multiplication, what we would realize is that actually doing matrix multiplication is only going to be possible when the number of columns of the first matrix equal the number of rows of the second matrix. And another thing we would notice is that the resulting matrix is going to have the number of rows equal to the number of rows of our first matrix, and the number of columns equal to the number of columns of our second matrix. I'll summarize this on a future slide, but while we're sort of doing this example out. So we know that we can actually do this matrix multiplication because we have, the 2 here and the 2 here. And the result is going to end up being a 3 by 3 matrix. So one thing I like to do is just sort of first recognize that this matrix multiplication is in fact doable, and then actually, write what the sort of final resulting matrix, at least its size, will be, and then I can start filling it in. And then again, if we were to sort of go back and look through that algorithm, or the formula, I should say, for computing matrix multiplication, one way we can sort of speed up the process without having to write out all of the steps every single time is to sort of take the first row. So let's say we want to know the result that's going to go in the first row, first column of the resulting matrix. So, one thing we can do is take the first row of the first matrix and multiply each of its elements by the first column of the second matrix. So that will end up being, in this case, 1 times 1 plus -2 times -1. Okay, and that's sort of a lot of stuff to go in that position. So maybe I'll actually kind of write that down up here. So 1 times 1 plus -2 times -1. And that's going to go right there. Let me erase all this so I have an actual spot to put that number. So the result here is going to be, I guess, 1 plus 2, which is 3. And you can go back and check with the definition of matrix multiplication that we laid out earlier that this does in fact work. And this is a little bit of a quicker way to go through this. So if we wanted, let's try again for another one. If we wanted to get the first row, second column of the result, we'll take the first row, which again is that 1, -2, and multiply the components of that by the second column of the second matrix, and sort of add up those results. So in this case, that would be 1 times 2, which is 2, plus -2 times 3, so that would be 2 minus 6, or -4. So we can kind of continue this process. The third, the first row, third column, we're going to take that 1, -2, and multiply it by the 0 and the 4, so that'll be a -8. And then we can kind of proceed. So our second row, first column, we'll go to the second row of the first matrix, first column of the second matrix. 3 times 1 plus 0 times -1 gives us a 3. And then 3 times 2 plus 0 times 3 is a 6. And then 3 times 0 plus 0 times 4 is a 0. And then finally, moving down to this last row, third row, we'll get 4 minus 1 is 3. 8 plus 3 is 11, and 0 plus 4 is 4. So this is the result. So BA equals the 3 by 3 matrix, 3, -4, -8, 3, 6, 0, 3, 11, 4. Going back to the previous slide, I'll remind you that AB was a very different matrix, right? So here was AB over here. Not only are the numbers in it different, but it's a completely different matrix in size, right? This is a 2 by 2 matrix, whereas BA is a 3 by 3 matrix. And again, the numbers are completely different. So one thing we notice here is that when it comes to matrix multiplication, AB is not necessarily going to be equal to BA. So this operation is not commutative. And we will, again, state that a little bit more formally later and remind you of it later. Not only will these results potentially be different, but there are instances where AB might be defined and BA is not even defined because the sizes of these matrices don't allow for that. So just something to keep in mind that we are probably not super used to when we're sort of working through algebra and calculus and working with numbers and functions and variables. We are sort of free to rearrange how our multiplication works without actually changing anything. In this case, when it comes to matrices, we cannot do that. And that's actually going to be something that comes up a lot in this course. You're going to find yourself potentially wanting to rearrange the order of matrix multiplication, but it's again not something we can do in this case. Let's do another quick example here. So let's say we have the matrix 1, 2, 3, 0, 1, 4, 2, 0, 1. I want to multiply that matrix by this other matrix here, which is another 3 by 3 matrix consisting of mostly zeros, but then we've got ones in what we call down the diagonal of this matrix. So if I were to circle that, you'd hopefully see why we call that the diagonal of this matrix. So let's go through our matrix multiplication with this matrix here. It's a special matrix that I will name in just a minute here, but I just wanted to show you one of the reasons this particular matrix is special. Okay, so I'm going to do that sort of quick. Again, just a quick check. This is a 3 by 3 matrix. This is also a 3 by 3 matrix. We are allowed to actually do this multiplication because these two numbers in here match. And the result is going to be a 3 by 3 matrix as well. So going through, we take, again, this first row and this first column and multiply their components and add them together. So we would get just 1. And then kind of working our way through, you would see that we'd get a 2 here and a 3 here and a 0 here and a 1 and a 4. And I'm going quickly here, but certainly pause the video and take your time and go through this. If you need to go a little bit slower. What we end up seeing here actually is that the result is just that original matrix A again, right? So A times this special matrix is going to get us back A itself. We call this special matrix the identity matrix. So the identity matrix of size n by n is denoted by I sub n, or sometimes we'll just write I. It has ones on the diagonal and 0 elsewhere. So some examples are I2, the 2 by 2 identity matrix, I3, the 3 by 3, and this should say I4, typo there, I4, the 4 by 4 identity matrix. And again, a lot of times in practice, we don't actually include those subscripts. We'll just write I, and it's sort of implied that it is the size it needs to be for whatever problem you're working on. And so again, that sort of identifying that property that we saw on the previous slide, the fact that if A is an n by n matrix, then A times I sub n. We didn't do the other direction, but it would be also equal to I times A, I sub n times A. So in that order, which is meaningful. Again, matrix multiplication is not commutative, so this is meaningful to reverse that order, and that gives us A. I've alluded to this already a bunch, but just to make it very explicit. So when can we actually multiply matrices? When is this defined? We can multiply matrices only when their shapes or sizes are compatible. So if A is an m by n matrix and B is an n by p matrix, then AB is defined and has shape or size m by p. More specifically, when constructing the product AB, the matrix A multiplies the columns of B. Therefore, the number of columns of A must equal the number of rows of B. When this is met, the number of rows of AB is the number of rows of A, and the number of columns of AB is the number of columns of B. Again, just kind of reiterating something we were noticing earlier. A few properties of matrix multiplication that I'm just going to state here and not actually going to go through any sort of a formal proof. If A, B, and C are matrices such that the operations are defined, then we have associativity. So A times the product BC is equivalent to the product AB times C. And we also have distributivity. So we know we can add matrices. And so what we're seeing here is that we can kind of distribute matrix multiplication into a matrix addition. So A times the sum B plus C is equal to AB plus AC. And then the other way works as well. A plus B times C is equal to AC plus BC. Let's do a few more examples. So this example is labeled zero divisors. We'll see why in a minute. We have these two matrices. They're both 2 by 2 matrices, A and B. Let's look at A times B. So working through that. Okay, so we'll get 1 minus 1, which is 0, minus 1 plus 1, which is 0, 1 minus 1, which is 0, minus 1 plus 1, which is 0. So in some sense, this is the sort of zero matrix, which we sometimes write as just like the number 0. So what we're seeing here is sort of like A times B equals the zero matrix. What we notice is that neither A nor B themselves are actually the zero matrix, and this is something that would not happen in algebra or calculus with regular real numbers or variables representing real numbers. We know that one of the really important properties of real numbers and sort of algebraic terms is when you multiply two terms together and get 0, you know one of those two terms has to be 0. And that is not the case, as we're seeing here with matrix multiplication. And then we have another example here labeled cancellation fails. We'll see why we call it that in a second. So we've got A, B, and C. Let's look at AB and AC. So first AB. We get 1, 0, 1, 0. And then let's look at AC. So here we get 1, 0, 1, 0. We get the same thing. And what we're seeing here is that AB equals AC, but B does not equal C. And again, this is somewhat unusual if we're thinking about algebra and sort of functions or real numbers. When we multiply two terms like this, when we're just talking about real numbers, we have this concept of being able to sort of cancel. So, we might think, oh, the A and the A can cancel and we'll just get B equals C. But here's an example sort of showing that that is not the case, that B does not equal C, even though A times B equals A times C. So summarizing some of the things we saw in this video here to just sort of caution you that even though the following properties hold for real numbers, they do not generally hold for matrices. So commutativity, in general, A times B does not equal B times A. Cancellation, if AB equals AC, that does not necessarily imply that B equals C. And zero divisors, if A times B equals the appropriately sized zero matrix, this does not necessarily imply that A or B are the zero matrix.